Also not very difficult. Were you Lee? Were you able to get question 4?
Yes. But it's okay, we can do it on the tutorial.
No, did you watch the video?
I did, but I can't understand.
Story of your life. What? In number 4? There's an MV squared in it. What? What is? It is. It's just a hard one. Okay, resistance. Have you got that? The problem with making coffee is then you run into other teachers. And this is a problem, because then they come to you with their problems. Stephen, I can't download this YouTube video. Show me how to download a YouTube video. Teachers. Right. Resistance. So, in the last lesson we saw what current was, but we can actually define current using a rate. What I mean by that is we can actually say current is the rate of change of charge per time. But of course that's not surprising, because the formula I gave you in the last lesson was Q equals IT. So of course I equals Q over T. So current is the change in the charge per unit time. I just said we have it, I know, but write it down again like this, please. Thank you, Bruce, thank you. Such a good student. Good student. Got that? Yeah. Okay. Next. Next. Come on, dudes. I don't think that'll help Lee. There we go. Now, this is a new term, voltage. So, voltage is kind of like potential energy. It's an electrical potential energy. And what we mean by voltage, it's per charge. Who the heck's calling me? Is this another teacher? I don't know who you are, so I'm not talking to you. Okay, it's potential energy per unit charge. And it's measured in joules per coulomb. So, for example, if I said something is 1 volt, then what I'm saying is that means it has 1 joule of energy per coulomb of charge. So, if I have a charge of 1 coulomb and there's a voltage of 1 volt through that, that 1 coulomb can actually do 1 joule of work. Now, how can it do this work? Well, there's many ways, but you know, electricity is a very important way to do work. Okay, continue. Yeah. So now we have current, now we have voltage. So now we can define what resistance is. Now, resistance of a conductor, it measures how difficult it is for the current to travel through the conductor. So you know a conductor has low resistance and an insulator has a high resistance. The unit we use is the ohm. And when we say a conductor has a resistance of 1 ohm, what we mean is 1 volt of electrical energy was lost to heat. So when 1 amp when 1 amp passes through the resistor. So I'll just, before you continue writing that, I'll just try and draw that to help. So let's say we have here 1 amp, and this is 1 volt. So when this 1 amp moves through it, if it wanted to, it could actually do 1 joule of work, if it wanted to, because it has 1 volt. And remember, 1 volt is 1 joule per coulomb. But this material has a resistance of 1 ohm. This means that for every amp that passes through it, this 1 volt is lost. So for example, if it had 10 volts, if it was 10 volts to begin with, and at the end it came out as 9 volts, then it meant that there was a resistance through it of 1 ohm, that it lost a volt, a joule per coulomb. So the resistance is not good because you're losing joules per coulomb. Yeah. This definition, yeah, I think if you try to understand it, it will be easier to remember it for the exam. Resistance is how difficult it is for the current to travel through it, and 1 ohm means 1 volt was lost when 1 amp of current passed through it. So, in other words, resistance reduces the voltage, and voltage is energy per coulomb. So resistance reduces the energy that can be done, the work that can be done per coulomb. Got that? No, I see people writing. Got that now? Bruce? Okay. Got that, Bruce? 2 words. Okay. Continue? Yeah? Alright. So, The following picture will help you explain the relationship between voltage, current, and resistance. Okay? Voltage, current, and resistance. I think this is pretty clear. So, whoops. No, this is a very important picture. So, the resistance is making it harder for the current to do work, because the current is losing its ability to do work, because the voltage is being wasted. Voltage is being wasted, pushing the current through because of the resistance. That's what's happening here. Okay. Comics aside, how can we measure voltage? So what do we use to measure voltage? A voltmeter. That's what an old-fashioned one looks like. A classic voltmeter. I just need you to write this vocabulary down. So we measure voltage with a voltmeter. Oh, there is another word for voltage too, which I should tell you. Say again? Potential difference, PD. It's another word for voltage. So we measure potential difference with a voltmeter. You write that down? Okay. So, what do we measure current with? We measure current by using an ammeter. That's what that looks like. Yes. OMG. You can join, but you're not getting any attendance.
It's fine.
Okay. You are 1 hour and 19 minutes late.
Yeah, today, wow, about 12 and a half.
Really?
Yeah, I joined, I got about 8 a.m.
You got the bus at the normal time?
Yeah.
8 a.m. Wow. Amazing. You're coming from where? Clondalkin or Tala? 24 is Tala. But
I don't have any chance. I have to go down.
no, it's okay. Calm down. Calm. I thought there's a Lewis in Tala.
What?
A Lewis. You know Lewis?
No.
Tram.
Oh,
You know the tram?
no.
You see it in the city centre. Is there not a tram in Lewis? Is there not a tram in Tala? Could you not take something other than the bus? You can only take the bus? No other options. You could cycle. You could ride a bicycle. I think it would be faster. Yeah. Anyway, that sounds bad, Jerry. Sounds bad. Okay, continuing. You got that? Yeah. Okay. So next one. How do we measure resistance? With a resist meter? No. No.
Calculation.
You could use a calculation, correct. But there actually is a machine to measure it. It is not a resistor.
No, it's not. I have resistor. Google. Real. Ohmmeter. You use an ohm meter. There it is there to measure resistance. Now, Bruce said you don't need to do this. That is true. In fact, we don't use this machine because it's not very accurate. Yeah. Tired and hungry. How do you eat breakfast?
Ah, look how small that is. That's tiny. That's not breakfast, that's just to get me ready to eat breakfast. That's pre-breakfast. Okay. Continue?
Yeah.
Yeah. So as Bruce was saying, which is an important point, we can calculate the ore. We don't actually need to use this, and we shouldn't really. We'll not use an ohm meter. We will use a voltmeter. We will use an ammeter. But we will not use an ohm meter. Now this is important. An ammeter requires current to flow through it. A voltmeter measures the voltage between 2 points. What I mean by that is, if I want to measure the current, what I have to do is put the ammeter, let me draw the picture of it, in the flow. However, if I want to measure the voltage, I clip 2 wires around my current. I draw my voltmeter again. There's my voltmeter, that measures voltage, that measures current. And I can measure the voltage from here to here, but really I'm only able to measure the difference in the voltage. So for example, if this was going at 6 volts and then out here it came at 2 volts because there was something going on here, like a light, then the voltmeter would say 4 volts. Yeah, so I can only measure the voltage between points. So this is why we call it a potential difference as well. It's the difference is what I can measure. Anyways, we will talk more about this later in the chapter, but it's worth remembering. Ammeter, voltmeter, like this. Okay. In other words, voltmeters and voltages are always between points, whereas an ammeter are always at the point. And I showed you on the diagram already. That should say triangle. The following triangle will give us the relationship between VI and OR. This is it. You might have seen before. So this can tell me voltage is current multiply resistance. Current is voltage over resistance. And resistance is voltage over current. So, just add this triangle to your notes. It's the VI-OR triangle. Where have you seen a triangle like this before?
In my presentation.
Weird. Where have you seen this before in my class? Yeah, distance, speed, time. I know, I believe that. You took a while because you were still relishing in the fact how awesome you were. Right. Continue? Okay. So let's have a look at our first example. An ammeter measures 250 milliamps when a current flows through a resistor. The resistor is a light bulb, so something like that. The voltmeter is placed around the light bulb and the voltage measured is 220 volts. What is the resistance offered by the light bulb? Okay, so I think you can do this easily. Having a look at the triangle I gave you, what do we get for the OR, please? What you get, Lee? Lee? Correct. Yes. So, OR equals V over I, which equals 220 over 0.250, which is 880 ohms. Again, I was just using this triangle. Is that okay? Happy with that? Right, next one. A 6-volt battery is used to power a toy which has a resistance of 2 ohms. Okay?
So the voltage is 2 volts, the resistance, 6 volts, the resistance is 2 ohms. Question 1, part A. What is the current? So what's the current here? V over R, 3 amps. Happy? B. If the toy was left on for 1 minute, how many electrons flow from the battery into the toy? Okay, so we have Q equals IT equals 3T equals 360 equals 180 coulombs. But I want to know how many electrons is that. Ne equals 180. So if I just take 180 and divide it by E, the charge of an electron in size. What is 180 over E? Monica, you have that constant on your calculator already.
1.123.
1.123. Yeah.
And 10 to the power 21.
Electrons.
Yeah.
Now, because that's a big number, please divide that by Avogadro's number so we can get it in moles. Moles of electrons. So that's 1.88 millimoles. Continue. Lee, continue. We have this. C. If the battery is replaced with 12 volts, then how does the current change? So, V is 12. I, we don't know. And R, we don't know. Well, come in. You are 1 hour and 29 minutes late. So what happened to you?
2 hours.
This sounds like a similar story to Jerry's.
I walked here.
You walked here? From where?
Half.
Where's Half? What part of Dublin is Half?
Wait, halfway from here.
Yeah, but where are you coming from?
I don't know.
Do you know where you live?
Yeah, do it now?
What's Dublin 12? No Irish person refers to Dublin by its numbers. Dublin 12 is Crumlin. Oh, that's not far away.
I'm leaving Dublin.
You live in Dublin 12? How do you get here? Walking?
But walking from is far.
It'll make you strong. Okay. So, the problem here with the last one is we don't actually know the or. Now, for this question, yeah? What were you going to say? Yeah, for this question, we don't know the or. We only know what the voltage is. We can assume the or is about the same. Although, technically speaking, it's not. The or isn't something which is constant. Sometimes it's roughly constant. In this question, I tell you to think of it as a constant. But the or changes just like the V changes and just like the I changes. What's wrong, Monica? You look so unhappy with me. If you have a question, ask me. It does not. It does not. It's just that the resistance appears fixed over a suitable range of voltage and current. But if you increase the voltage and the current, or even if you just increase the current enough, you'll see the or will start to change. It just appears to be constant within a certain range.
But the three of them actually change together. It's just the or is the one that changes the slowest, the least, yeah. So, here we have V equals 12, I we don't know, and or still equals, what did I get previously? 2, was it? So, the I is V over or, which is 12 over 2, which is now 6 amps. Yeah? What did I get previously for the current? 3 amps?
3.
Yeah. So the result of doubling the voltage was to see a doubling in the current, provided we consider the resistance as unchanged. Now that's a big assumption. It is a big assumption, you know, because if you were talking about distance, speed, and time, if I change the distance, I would see the time change, as long as I assume that the speed has stayed the same. But it doesn't have to be the same. The speed can change too. All three of them can change. But usually the speed shouldn't change if I just change the distance. But who knows, maybe if I make the distance bigger, then I make whoever's driving the car want to drive faster. But I can say it's roughly the same, you know. Okay. I think that was the end for that part, was it? Yeah. So, you may assume the or is constant. This is not always the case, and in fact, it's a law. And we'll see that in the next class. Perhaps I shouldn't even say it's a law. It's an observation. Okay. Right. I think, yeah. Not Coulomb's law, Bruce. Did you say Coulomb's law?
Yeah.
Oh, you said Coulomb's law. Your impersonation of Bruce is quite good. Right. So I gave you, as you can see, we started a new chapter, so it's not too difficult at the beginning, except for that question 4. You can start the next worksheet, but Monica and Lee, or anyone else, if you want to put your headphones on to have a look at how I did number 4, if you just can't wait till you get home, oh, you already did, and it didn't.
You got the wrong answer.
No, I got the answer.
You got the number without the 10 minus 1, is that
Like the answer I got is I'm assuming the answer present because I didn't keep track of how the unit changed.
That's
But
perhaps a problem.
The answer is,
Tiny. That is correct answer.
but my answer is the same value eventually. So if I
You do appreciate that there's a huge difference between 1 meter per second and 1 micrometer per second.
I do.
You know there's a difference between the two. Good. Okay, but then just go on to the next worksheet then, and we can do this one in the tutorial. Yeah.
Sorry, what's this thing that you usually do when you add an E to the big N?
Add an E to the big N.
Add, multiply the big N with E.
Oh! So, if I have, say, 1 coulomb of charge, that could be made up of many electrons. Each electron has charge E. If I multiply this by N, that's the total charge of all these electrons. I'm just saying it's equal to the charge I have. I'm just trying to figure out how many electrons I have. So I take my charge and divide it by the charge of an electron.
Once we get the number, how do we find the speed?
Which part are you on?
The number of electrons.
After
Watch the video again. I'll give you an outline, okay? This is the concept. So you have your copper wire, and you don't need to look at the full wire. You only need to look at how much you have in 1 second. So we're just looking at 1 second of time. So we imagine that it's only this part that we care about, because all the electrons in here, they are what exit in 1 second. You have the formula distance, speed, time. So what does distance equal? Speed multiplied by time. But if time is 1, then what does distance equal? Speed. So this will equal the speed of the electrons, this distance, which I'll call it v. Okay? Now, I tell you in the question we have 1 amp. So that means the total charge, Ne, is equal to 1. Okay? Now, this is something we know, this is something we know, so we need to work out what the N is. But the N will depend on how big this is. Obviously, if the V is bigger, then the N will be bigger, and likewise. So if you can write the N in terms of V, then you have an equation with V in it. So basically your next job is to figure out what the N is, and the answer you get should contain V, because you don't know what the V is. So to work out this, you'll need to know some things about the copper. You'll need to know the volume, right? And you also need to know the density. And you also need to know how many atoms. And then I tell you that each atom of copper has 1 free electron that can be used to carry the charge. So I think, take this as a starting point, ask yourself, how do I work out the N? And then once you have a formula for N in terms of V, you can go back to this and solve for V. Just like that. I don't give you V. I want the V. That was a bit of a distraction. The total length is 1 meter, but we are only concerned about the piece that exits in a second. I feel like, I think I said this in the video, I should have perhaps deleted that fact that the length is 1 meter, because it's not actually important to the calculation. It doesn't matter if we have 100 meters of copper, we're only looking at a second worth of copper. Yeah? Sean and Jerry, do you know what's going on? Or is this too difficult because you missed the first class? You've learned it before? Oh, Bruce, you have the worksheets for Jerry, don't you?
Yeah.
Did you give it to him? And Sean, Monica, did you give Sean his? Okay.